Welcome to This Explainer. Okay, today we are decoding the sheer biological magic running inside you right now. If you want to demystify exactly how our bodies communicate on a cellular level, you are in the exact right place. We're going to break down this incredible alphabet soup of receptors and neurotransmitters. All right, let's dive into this. Have you ever actually stopped to wonder what exactly causes your heart to beat or your lungs to breathe without you even having to think about it? It's pretty wild. These massive, involuntary life functions don't just happen by magic. They are strictly controlled by tiny chemical messengers zipping around inside you every single second. Here is our roadmap for today. First, chemical messengers. Then, locks, keys, and hackers. We'll explore the fight or flight system, contrast it with rest and digest, and finally wrap up with central nervous system regulators. We're building this step by step, going from the microscopic level straight up to major bodily systems. Let's get to it. Section 1, the body's chemical messengers. Let's start with the absolute basics of how your nervous system actually talks to itself. And this brilliantly illustrates the synapse. Neurons send electrical impulses down their lengths, but they don't actually physically touch the target cell. Instead, there's this tiny microscopic gap called the synaptic cleft. So the sending cell just shoots chemical messengers, neurotransmitters, across this gap. They float right over, bind to specific receptors on the receiving cell, and boom, the signal continues. Section 2, locks, keys, and hackers. Now that we've got that gap visualized, let's use a classic analogy to understand how medications actually hijack this setup. Think of receptors as locks and neurotransmitters as keys. In pharmacology, we have these things called agonists. An agonist is a drug that binds really tightly to a receptor to get a desired effect. When you take an agonist, it's essentially mimicking your body's natural neurotransmitters. It slips perfectly into that receptor lock, turns it, and triggers the exact cellular response we want. It basically acts as a synthetic master key. On the flip side, we have antagonists. Let's contrast those two. An antagonist doesn't turn the lock at all. It jams it. It's a drug that competes with other molecules to block a specific action at a receptor site. These meds act as lock blockers. They just sit right over the receptor, completely preventing your body's natural keys from getting in and doing their job. Now, what's really interesting about this slide is how clearly it shows an antagonist in action. Look over at that cardiac cell on the right. It's absolutely covered in beta receptors. Normally, adrenaline, your natural key, would bind these receptors and just spike your heart rate. But here, we see a beta blocker medication physically standing in the way, blocking the adrenaline from hitting those cardiac beta receptors. Because the locks are jammed, the heart rate simply doesn't increase. Moving to Section 3. Fight or flight system. Let's scale things up to look at the first major bodily system these microscopic locks and keys control, the sympathetic branch of the autonomic nervous system. So, the autonomic nervous system is all about balancing two main sides. You've got the sympathetic system, your classic fight or flight response, which gets you totally geared up for action. This is driven by adrenergic receptors and neurotransmitters like norepinephrine. And countering that, you have the parasympathetic system, your rest and digest response, which is driven by cholinergic receptors and acetylcholine. Right now, we're zooming in specifically on that fight or flight side. So the crucial point here is how this system breaks down into an absolute alphabet soup of receptors. Just look at this. Alpha 1 targets smooth muscle, causing blood vessels to constrict. That's exactly how pseudoephedrine acts as an agonist to magically clear up your stuffy nose. Alpha 2, interestingly enough, actually reduces CNS stimulation. Then we get to the betas. Beta 1 targets the heart. Give an agonist like dobutamine, and it revs the heart up. But use an antagonist like metoprolol, and it slows right down. Finally, beta 2 relaxes smooth muscle in the lungs, which is why an agonist like albuterol opens up your airways during an asthma attack. If you know the exact receptor, you know exactly how a drug is going to alter the body. Section 4, Rest and Digest System. Let's shift gears completely to the opposing side of our autonomic balance. Over in this system, acetylcholine, or ACH, acts as the body's natural master key. And just like a physical master key can open different doors, ACH binds to two very specific types of locks, nicotinic receptors and muscarinic receptors. Both of these receptor types bind to ACH and kick off those calming, rest and digest changes in their target cells, like lowering your heart rate and firing up your digestion. And of course, medications are designed to specifically target these rest and digest receptors,
We have nicotinic agonists like the nicotine patch, which bind to these exact receptors to help ease withdrawal. Then we have muscarinic agonists like pilocarpine that stimulates receptors to contract the ciliary muscle, which treats glaucoma. And we can't forget the anticholinergics, which are our antagonists. Ever worn a motion sickness patch? That's likely scopolamine. It blocks ACH right in the brain's vomiting center to dry up secretions and completely prevent nausea.
Section 5, Central Nervous System Regulators. For our final structural jump today, let's head straight into the brain to look at mood, cognition, and motor control. The central nervous system relies on an incredibly delicate balance. Take norepinephrine. It totally impacts your alertness, and imbalances are linked to things like depression and panic attacks. Dopamine is heavily tied to motor function and cognition. Mess with that balance and you see links to ADD and schizophrenia. Think of serotonin as your master regulator for sleep, mood, and temperature. And finally, GABA. GABA is basically your brain's brake pedal. It's an inhibitory chemical that calms the nervous system down, which is exactly why medications like gabapentin enhance it to control neuropathic pain. An excess or deficit of any of these drastically alters who we are in a given moment, and medications step in to help restore that crucial balance. Which brings us to a pretty wild final thought. How much of our daily reality, our moods, our heartbeat, our literal ability to breathe, is determined by a tiny molecular key slipping into a microscopic lock? It is honestly astonishing when you really think about it. The incredible power of pharmacology lies entirely in understanding this specific chemical machinery, allowing us to build synthetic keys and lock blockers that save and improve lives every single day. I really hope this visual breakdown helped clarify the complex alphabet soup operating inside you right now. Thanks so much for joining me on this explainer, and stay curious.